So I'm going to talk about fast, idiomatic, and elegant Elixir. The short version is recursion is your friend and you should be comfortable with it in a functional language. So I'm going to take you through it step by step. So what we're going to do is come up with a simple contrived problem, which is essentially summing integers in a list. So what we want to try and implement over this talk is essentially a sum function that takes a list of integers and gives us the result. As we'll see, there's quite a few ways to do that. So let's move on. So I saw on Twitter, I could never find the actual picture, but someone had actually posted code that looked like this, and I was a bit horrified. And I wasn't sure whether the context was do it this way or don't do it this way. Yeah, don't do it this way. But who can tell me what might be wrong with this? There might be more than one thing. Anyway, have a think about it.
Is it the if statement?
Well, yeah, that's not really idiomatic, is it? It's sort of, we can use function heads in Elixir to get rid of lots of, arguably ugly control flow. That's kind of nice. So, yeah, the if statement's probably not idiomatic Elixir. Anything else? You can Stack Overflow with this, yes. So it's not tail call optimized. So if you don't know what that means, don't worry. I'm going to cover that at the end of this talk. Basically, a Stack Overflow is where you use all available RAM. This will do that, and we'll see why. There's one other thing that makes this really slow. Can anyone spot it?
Yeah, because we're taking the tail of the list.
We are. That doesn't make it slow, though. The length, thank you. Who said that? Prize points for you. Length, we'll see why it is bad in a minute. But basically, length traverses the entire length of the list. So for a really big list, every time you're calculating one element, you are essentially traversing the entire list. So it's like an n squared quadratic problem. That's bad for where n is big, like 10. It's bad. So what's wrong? Yeah, it doesn't use pattern matching. So we could have got rid of the if with pattern matching. It's not really idiomatic. It looks suspiciously like Ruby. It's a bit hard to read, just because it isn't idiomatic. The length check runs, across the entire list of n items every time, and we're running that n times, so it's n squared. That's bad. And the recursion isn't optimal because we can use up the RAM, so we'll figure out how to fix that. So this is the obvious way to implement that, but under the covers, this Elixir is actually doing it the tail called optimized recursive way. So we'll see how it actually happens, and it ends up being faster, so read on. Nice, job done, but we can make it better. I'm pretty sure we can. So there's a bunch of other possible approaches. We can use reduce. There's 3 different styles of passing in the function for reduce. Essentially, if you don't know what reduce is, it's like inject in Ruby. Essentially, you're transforming that list into one single number. So map keeps the shape of the thing that you're mapping over the same. Reduce reduces it down to something smaller and changes the shape. So we take the list, we start with a sum of 0, that's the accumulator, and then we essentially add to that each element. Oh, that's true. It changes the shape. Cool. Yes. So these are the 3 different ways that are exactly equivalent. FN is the long way. Ampersand is the short way to make a lambda, and reference. Does everyone know what the ampersand 1 and 2 are in the second example? If you don't, they're essentially the first and second arguments of that function, which is exactly equivalent to the plus function. So down the bottom, we've basically said ampersand, here's a function, and plus arity 2. And plus arity 2 is a kernel function that's available to you. And it takes arguments in whatever position, so it doesn't matter, so we can just give it that function. So all of those things are completely equivalent. But reduce isn't the best way to do this. We can do it better. So recursion, you may have avoided in the past. So who comfortably uses recursion in Elixir right now? Okay, sort of a few people, but not everyone. So, initially I was scared of recursion simply because, Stack Overflows if you forget your base case or don't stop, it's kind of scary. And it's often slower. But in this case, it isn't. So just a reminder, lists are singly linked lists in Elixir. Anyone who remembers what a cons list is, that's what they are. Essentially, can you see my mouse? Yeah. Cool. So this this list of one element, which is 1, is equivalent to a list which has a head of 1, and the rest of the list is an empty list. So that's what it looks like under the covers. And then when you have a 3-element list, it is essentially, we'll see a picture in a minute, but it's the head and the tail, head and the tail, head and the tail. It's easy to see the picture. So it's super efficient to add and remove at the front of the list. It's super inefficient to add and remove at the end of a list or in the middle, what have you, because you have to traverse the entire list to get to the end. So keep that in mind with Elixir lists. So again, getting the length requires visiting every element to count up how long the list is. There is no shortcut. It's not an array. So if you can see under there, essentially each element in the list is a value and a pointer to the next part of the list, the next value, which is essentially the rest of the list. And at the end, it's basically an empty list, and that's when it stops. Does everyone get that? Good refresher, you're going to need to know this. So this is kind of nice because it lends itself to recursive solutions really well. So just a refresher on pattern matching. We've got a list of 5 items there. That gives you 1, 2, 3, 4, 5, great. And we can pattern match in the second one, the head and the tail of that list. So this returns the whole list, but when we've done that, the head is 1, and that's just the value, and the tail is a list of the rest of those values. That's going to be handy in a minute. Might look a bit weird if you haven't seen it before. Did that just turn off? Wow. All right, we're back. All right, so this is what the recursive, I'm going to call it a naive recursive because I call it that later. Yeah? Awesome. So this is like a recursive approach. The things that are nice about this is the pattern matching lets you handle the base case first. Now I really like that when I'm doing like TDD, and TDD is great for these kind of problems as well. Essentially you can handle and get out of the way the base case, which in recursion you have to handle, otherwise it's going to keep going forever. So that's pretty important. So the first thing you do is handle the empty list. And that means that you can write a test saying, do you handle the empty list? And I get 0. Awesome. That's pretty cool. Then we pattern match on the second thing down here on the head of the list and the tail of the list. And that handles every single thing, other state that it could possibly be except for empty list. That's great. So we take the head value and we add that to the sum of the tail value. So we're calling ourselves, that's recursion. And what we're going to do is pass the tail of the list in, take the head off, etc. But that has problems. But the benefits are write the base case first. It makes it hard to forget, because if you forget, you don't really stop the recursion ever. You isolate the base cases out from the main case, and you don't get any awkward if statements. It's pretty compact and easy to read. Does everyone agree that that's pretty concise? You can write it on 2 lines if you want. It's pretty cool. And it is actually faster than using enum. I'll do some benchmarking at the end. And you might be surprised at how much faster it is. But we have to make sure that we use tail call optimization. Who knows what that is? About 6 of you. Okay, so who's heard of tail call optimization or tail recursion? Isn't quite sure. Cool. Okay, we'll explain it. It's actually pretty simple. So this is the key slide. If a recursive call is the last expression, then, and it has to be the exact last expression. You can't come back for any stuff. And just to be clear, this is not the last expression. So the last expression here is actually head plus the sum. So we'll see what it really looks like when it's optimizable. So the compiler can then use a jump or a goto without pushing an extra stack frame. Now what that means is in order to keep the context so you can come back and calculate the value, then it has to keep it in memory and every function call has to go onto the stack. So you're using memory basically. So the summary of that is that tail call optimized recursive functions are super fast, don't use extra memory, they don't use any extra stack frames, so you never get a stack overflow. You're essentially going as fast as a C loop, give or take. But the one caveat is you have to pass all of your state along, all of it. You can't come back and do anything later. And we'll see why in a second. So this is what the tail call optimized recursion version looks like. So essentially what we're doing is we've got a little convenience, function header at the top. Does everyone know that if you've got multiple function heads, you can have an empty one to give you some default arguments? So if anyone is wondering why that doesn't have like a do after it, it's essentially setting up the template for default arguments. So all we're doing is saying when you just pass a list, we set automatically the accumulator to 0, which is the sum. So then we handle the base case, and because we're passing the accumulator along with us, then we have to essentially take the accumulator that's given to us, which at the start is 0, and return that. So our empty list case will work and just return the 0 that was defaulted to up here. Cool with that? And this is just the same, except we're passing the accumulator along with us every time, which leaves us with the sum being the final expression. There is nothing else to come back for. And we'll go into detail in a second. But essentially all we're doing is saying sum the tail, which is the list that we're going to calculate the sum of, and pass the new accumulator, which is adding head on the start of the list to the accumulator that you've got so far, the sum that you've got so far. So if you're wondering why I've called it ACK and not sum, is because ACK tends to be like the idiomatic way of doing it. Any kind of looping like this where you're collecting state, that's called the accumulator. So yeah, it would be nice to call it sum, but it'd also be confusing with the actual name of the function. So typically the default is to call it ACK because it's short for accumulator. So because we're passing all of our state along, then we don't have anything to come back for. And that's the whole point of it. It has to, essentially, well, the key thing is if you have the last line being just the recursive call, you're good. That's tail call optimizable. Okay, so this is the comparison. Is everyone good with that? I'll move on. It's just two of them together, just so you can see the difference. So why is the naive not as fast as the optimized one? And you might be surprised to know that it's a lot slower. So it's still quite fast, the naive tail, like recursive version, still faster than some. Yeah, so basically it's about the stack frames, and we'll see in a sec. So we have to come back all the way back. So it's essentially double the distance. So this may help illustrate it. So picture you've called sum with a 3-element list, 1, 2, 3. This is what the first call evaluates to in the naive version. So this is, we've said head of the list plus the sum of the rest of the list. Cool. Then we keep going. We've reduced the list by 1, and that's pretty important in recursion. You've got to always reduce the thing that you're recursing on, otherwise you'll never finish. Then we take the head of that remaining list, 2 plus the sum of the last item, then 3 plus the sum of the empty list at the end. Great. Now you'll notice that the result of sum of an empty list from the first version of that is actually 0. So what you'll notice here is that we don't actually have the answer to the sum. We actually have to take 0 and replace it here and then add it to 3. And kind of this is where we're popping off the stack and all of our function calls. And we've had to keep all of the state of these function calls around, so we can essentially put the 0 into here and add it to 3. Take the 3 plus 0, which is 3, add it to here to get 5, return 5 here and add it to 1, and then we've actually gone out once and then back once. So it's kind of double the distance of what we're about to see. So this is kind of trying to illustrate the evaluation on the way back. And only when we get back to the bottom of the stack, so we've gone out and we've come back, do we get the answer of 6. So the tail call is only half the distance. Essentially what we're doing, because we're passing all of our accumulated state along, we get the answer once we've seen each of the items in the list, basically. So the first call of this is we take the tail, 2 and 3, and we add that to the first accumulator. So add the head, 1, to the initial accumulator, 0. And we get 1, and we pass that into here, and so forth. Does everyone see how that's twice as fast, essentially? And then we don't have to come back for anything. So essentially what the compiler is doing is saying, oh, I can optimize this. You're taking all your baggage with you. We can just skip the last stack frame and just do a jump over to the next one with all of the stuff that you need. So once we get to the end, we've got the answer, and we don't have to go back. Does that make sense to everyone? It's kind of simple. Hopefully that's illustrative enough to help you reason about your own recursive code. But basically, if you've got the recursive call as the last thing in your function, you're cool. Just make sure there's nothing else there. Okay, so performance. So I did a 100, let me just fix that. I think it was 100,000. I'll give myself the benefit of the doubt. Could be 1 million, I don't know. Anyway, it's all just relative scores, because I did this quite a while ago. It might have got faster. You can run your own benchmarks. I might publish this in GitHub so we can. But basically, long story short, tail call optimized version is ridiculously fast. So 681 microseconds per operation across a very large list. That's pretty reasonable. So the recursive version is about, half the speed of that, essentially. So in the time that this bench fella gives it, it's only run 1,000 iterations, where this one's run for 5,000. That's pretty cool. Some better obvious Ruby-ish.
What's the iteration? The number of times it's run?
Or how big's the list?
What is the iteration column?
Oh, it's just, so bench fella, when you run it, essentially gives you, I think I had the code somewhere. Bench fella basically gives it an allotted time, so it's like 10 seconds or 30 seconds or whatever to run as many iterations as it can in that constant time. And then it calculates the average per operation. So 681 doesn't sound fast, but it's a pretty large list to do this. I can't remember what the other better and obvious and Ruby-ish are, but the Ruby-ish one was the one we saw at the very beginning. No, I didn't put it there, did I? Sorry. Where was it? There. Right, so that was the super slowest one because of length. So it's essentially quadratic. So for a 100,000 item list, we're running that 100,000 to see every element. And then for each one of those elements, we're running it 100,000 times to figure out the length of the list, which is pretty stupid. It's a pretty big number. So that's why this is ridiculously slow. And I think these were the reduced ones, the better and the obvious. They were pretty similar. So, but I mean, I was kind of surprised at how much faster just a hand-rolled tail call optimized version was. It was kind of an interesting exercise. So the length was the culprit there. N squared, that's pretty bad. So be careful when you're using length list. It does traverse, especially in a loop, it does traverse the whole list. So save it away if you need it. And I mentioned Exercism before, so that, it's a pretty good, small problems, friendly people to compare your answers with. Until you submit an answer, you can't see other people's answers, which is kind of nice, stops you cheating. But they're nice to try on the bus or the train or what have you, and compare your answers and have conversations and so forth. So I made an Elixir Sydney team. It's linked off the new website, so check it out. Thanks. Any questions?
Is there any instances where tail call recursions is worse than the normal recursion that you showed, like the first example?
I don't think so.
What do you mean in terms of performance?
Yeah, so let's say you're benchmarking
Yep. I didn't check it on a small list, but obviously it's going to be very similar with 10 items in the list. It's not going to make much difference. That's why I had to make it really big to get obvious differences.
It's hard to say if it would give any negative.
Well, I mean, with the normal naive recursive approach, you're always doing twice as much work. You're going out and you're coming back.
So why, I'm kind of wondering why this one is, the VM is optimizing when you're doing tail calls. But
It's the compiler, yeah.
it's not really sort of discouraged that you're just doing regular recursions.
Well, I mean, it should be, and you should be aware of how much memory it would be using on a really big list because you're having to keep all of those stack frames for every single item in the list around in memory. So you can run out of it, and that's where you get stack overflows and so forth.
There was a post on the mailing list. There was a post on the mailing list a couple of months ago where someone claimed that actually, I don't know if you can call it list recursion, but for small, let's just say small loops, it was actually faster to be non-tail recursive.
Right. Did they say why that was?
What is small?
But I imagine if you use an actual array, then you can stay inside the L1 cache, which is probably helpful.
Yeah, but this is specifically lists, which is not an array. So, yeah, but I think if it's a really small list, then it doesn't freaking matter. If it's a 10 item or a 100 item list, it really doesn't matter. It's irrelevant. Like the time differences will be.
Random number of items in your list and your function gets a whole lot over time, the average performance might be a problem.
Oh, potentially, yeah.
If your small lists are very slow and you're having a lot of small lists come through this one.
And then if you're getting different behavior characteristics and wildly different lists of tiny sizes and large sizes, then you could split based on how big that size is on your implementation. But yeah, I think typically when it's small, it's going to be kind of irrelevant unless you do it a lot. So, any other questions?